Okay, so the data link layer is one of the simplest layers to cover, which is why I'm going to try and cover it in 20 minutes. We'll see how that works. This is referred to layer 2, and where the physical layer is layer 1, and it's just transferring a datagram from one node to the next, and assuming that they're directly connected. Typically, it's either Ethernet on the last hop in either in your home or in your at your workplace, or wireless links, so 802.11 or Bluetooth. A layer 2 packet is called a frame, a data frame. This is a picture of what it looks like. You have a directly connected computer to a router, and in order to get a frame from one end to the other, you're basically using a data link layer protocol, and you are encapsulating the application payload, the transport header, the network header, and the link layer header is at the very outer part of this. And this is the payload that gets sent across the physical link. And then on the other side, you get this frame that's got all of these things, and then you can pull off the layers one by one, and then look at that packet, and then forward it on to the next hop. So that's the protocol stack picture at the link layer level. All of this is done typically on your network interface card. And now this is really old, but it's still, I don't even know what interface that is, but basically all of this stuff is integrated in your laptops and your phones, but this is all done in the framing protocol is all implemented in hardware now. Some functions that the link layer provides: flow control, so that you're not overflowing the base station, for example. Security, and this is mainly for broadcast data link layers. So you've seen when you're selecting access points, you see the ones that are open and unsecured and the ones that are secured. The difference between those two is whether or not you're running something like WPA, which is providing you data link layer security. So it's security between your laptop and just that base station. It's only a hop-by-hop protocol. As soon as the base station decrypts your data link layer frame, it's then unencrypted. So that is what, when you're selecting a Wi-Fi hotspot, that is what's, even when you're selecting a secure one, it's only securing the broadcast. It's not securing anything beyond that. And this is one of these things where the end-to-end principle comes in. Like, if you think you are secure using HTTP over a WPA protected hotspot, you're basically fooling yourself, because on the other side of that hotspot, all of your stuff is unencrypted. And this is when we get to the TLS and HTTPS part of it, the only way you can provide guarantees on end-to-end security is with an end-to-end protocol, which is what TLS and HTTPS is. So we'll get to that later. It's important to note that WPA is only a hop-by-hop security. It's only encrypting it on the one hop, and then it's decrypting it on the other side. Okay. The error detection and correction is done at the link layer. And then medium access and quality of service. How do I mediate when we've got a whole bunch of laptops trying to access that network? What is the protocol for deciding who gets to send next? And if you are interested in this, this is where the networking course comes in, because media access control is a big topic in wireless networks. Another important function is demultiplexing to the upper layer protocol. So back in the day, when we used to have a dozen different data networking standards, then in the link layer had to support whether or not you are on an IP network, on an SNA network, on a DEC network. And so this demultiplexing will route whatever data link layer frame is to the actual network layer that it's being sent on. Almost all of the traffic you will find on this campus is IP. So this is something that's just here for historical purposes now, because everything is using IP as a network layer protocol. And so here are some Ethernet protocol types. And so almost everything is 800, hex 800, or this is octal 800. I forget which one. There is some ARP, which we're going to talk about next. That's not IP. So pretty much as everything is. This is actually important, and you'll see when you get to the cloud and you see all of these networks that people are instantiating left and right in the cloud. how is that actually happening? There isn't a guy over there plugging stuff in and taking things out. As it turns out, what they're doing, sometimes they're tunneling packets over different Ethernet protocol types. So this is a way you can use these protocol types to do virtual networks. So virtual private networks can be implemented using data link layer techniques, and we'll get to virtualization soon. But all of these virtual LANs that Portland State uses, these are all data link layer tricks that are being done with the protocol type. And this is just an aside for this. But this is the reason why knowing a little bit about the data link layer helps you understand how the thing works on the back end for a cloud provider. The other thing that it provides is framing. So you have to encapsulate the payload, as we were mentioning earlier. This is a picture of an Ethernet frame. The destination address and the source address, these are hardware addresses that we're talking about, not IP addresses. The data inside might be an IP packet, and that would have your IP source and IP destination. But this is really the outermost doll of this packet. Let's see. So the other piece of this that I haven't talked about is the CRC. This is for error detection. So if this is like a checksum at the end, where if some bits get garbled from me to that base station, the checksum will reveal it, and then we'll ask for a retransmission. Okay, one of the things about the destination and the source hardware addresses is that these are globally unique, and they are bound to the manufacturer of that hardware. Now, for your ARP labs, if you are running a Linux machine in a VM using VirtualBox, that's distributed by Oracle. Oracle has been given a range of hardware addresses for it to use in its virtual machines. Because one of the things about virtual machines is that you have to pretend that virtual machine has everything. It has a virtual network card, virtual IP address, it's got all the virtual things. And so in order to get globally unique MAC addresses, Oracle has their own set of hardware prefixes that it will send out data frames for. So your virtual machine is actually emulating an internet connection to the host that it's running on. And that is done using IP protocols and data link layer frames, as it turns out. Okay. One of the things that you can see is that there are two different kinds of addresses. You have the MAC addresses, the hardware addresses, and then within it, you might have IP addresses. The reason why IP decided to decouple the two of them is that the hardware address is flat. It's not hierarchical. If you tried to route on everybody's MAC address, immediately you have a routing table that's got 4 billion entries into it, right? Because there's no organization. Like if you go and do a survey of all the MAC addresses in this room, like there's no order to it, right? Like some people have different hardware vendors. So this is where decoupling from the hardware really matters, and this is why the IP address is a logical address, and it's hierarchical. And the ability to group IP addresses together into one sort of prefix is what they call it. This is what allows you to manage machines much more naturally and manage routes to them much more naturally. And we'll cover this Wednesday. Okay. So I am going to cover ARP, which is one of the two main data link layer protocols that we're going to cover here. So if I have this laptop and it comes up on this network, if it has a packet that it wants to send to Google, how does it actually put a frame onto this data link that allows this access point to then send a packet to Google? So this is the first step. Because hop-to-hop communication is done by hardware addresses, the first step my machine needs to take is to figure out the hardware address of that thing. And so that's what the ARP protocol does. The ARP protocol says, hey, I know where my default router is. Say I've done something that I know I need to send a packet through the default router to Google. I need to know what is the hardware address of the default router, because I need to construct that frame. I am trying to construct this thing, but I have no idea what the hardware address of that access point is. So the thing that it will do is it will ARP. So ARP is a protocol that allows you to resolve the hardware address of anything on the network. So here's an example. Here's my laptop A, and say this is a base station, not another computer. And this is my hardware address, but I don't know this hardware address yet. And so the ARP protocol allows A to determine this unknown MAC address, given that it knows the IP address of the person that it wants to send it to. And so the way this works is that A will do a broadcast over the network, so over the clear. It broadcasts saying, hey, you know what? I need the MAC address for 131.252.220.24, and it sends it to everybody. And then all of the machines will receive this query. And when B receives it, it sees that it actually is the person, or the machine, or the router that it's being asked of. So then it knows its hardware address, and it will return it directly to A using A's MAC address. So it knows, because B got this request from A, and A has to, in its data link layer frame, A has to put its own hardware address in there. It uses the broadcast destination address, but it does put its own MAC address in the initial broadcast, ARP broadcast. And then what B will do is it will receive it, it will note that it came from A, and then it will send back a data frame to A's MAC address saying that this is my hardware address, and that's me. Okay. And then A will cache that. It will actually create this ARP table inside of its operating system. And this is soft state, meaning that it'll time out. So unless it is continually refreshed, this mapping will eventually time out. And this is very similar to DNS requests that we'll cover later. So a lot of the internet state is meant to be soft state, to be continually updated, just to make sure that all of these things are consistent. Okay. On a Unix system, you can do an ARP-A, or you can go into the /proc. So /proc is a way of getting all the different parameters out of the kernel to figure out what your ARP table looks like. And these are the directly connected machines to you on this network that you have seen. So those are the two commands to pull out. And I think I have you do this in your lab. Okay. So what happens if A and B are on two different networks? So say B is Google and A is your web browser, and there's a router in between. And so what happens here, assuming that the router here has two interfaces, so every router has to have at least two interfaces to be able to route from one LAN to another. So here you have a picture where the person in the upper left is trying to send to the person in the bottom right. There are two ARP tables in R. One ARP table takes care of this LAN, and another ARP table takes care of the other LAN. And so this is the way it works. If in the routing table for A says it wants to send a packet to Google, but it's not directly connected to Google. So it says, hey, where is my default router? And this is the default router that gets initialized. And so I know I need to send my frame to this default router. And so A creates a datagram with source A and destination B. And then it checks its route table, and it sees that B is not on its network. So then it uses ARP to get the router's hardware address for this interface, because it knows it needs to send an IP packet to this router so that it can get to B. So that is the next step. And then when R says, this is my hardware address, A can then send an IP packet with this hardware address as a destination, this hardware address as a source, and the payload is a packet from A to B. So it creates that data link layer frame. It sends that frame to R, and then R is going to receive the frame. It's going to pull out the frame and take the IP datagram that's in it, and then it sees that the destination is B, and then it looks up in its own route table, and it sees that B is directly connected to it. And so what it does is now it can just ARP for B to find out B's hardware address. So it sends an ARP to LAN 2, assuming that it's not in its ARP table. And then it creates a new frame containing the A to B packet, but it's a data frame that has this as the destination and this as the source. And then it delivers it to B. So one of the questions that you might ask is that what prevents C from responding to A's initial ARP request for this route R? Like C could say, you know what, I'm actually this IP address. Is there anything so for example, if I put up a base station that says PSU secure, what mechanism exists for you to see whether or not that's legitimate or not, to prevent me from responding to all of the ARP requests going into that base station? Do you think there's any way of preventing that? No. So it turns out that this is an issue. It's completely unauthenticated. And this is where an adversarial analysis of every protocol and every piece of, for example, software that you're using needs to be done. And so here is a picture of an ARP spoofing attack that has no defense, has limited defense. So here you are talking to this base station, and this particular person starts to bomb the default router for a little while, and then listens for broadcasts that ask for the hardware address of that base station over there. And then what you would do is you would just say, yeah, that's me. And then on the back side, you would start forwarding stuff through you to the default router to the outside world, and then on the way back, you would capture that and then replay. So this is a man-in-the-middle attack. And so this is the reason why you would do something like HTTPS, some end-to-end encryption, because the end-to-end security can only be done with an end-to-end protocol. So that's just an aside, just because I like to do security. Okay, and I'm going to stop there because now I'm really out of time, and I'll pick up next class. Okay, so we left off on DHCP. We're just going to finish the link layer really quickly and then move on to the network layer. DHCP is the other significant layer 2 protocol. And it answers this question: how does a host get an IP address in a subnet? When you first bring a computer onto a network, you have to have some way of getting the network configuration. And typically, you would like that to be done automatically. You wouldn't like to have to boot up your computer and say, what is my IP address? What is my DNS server address? This, that, and the other. So you could, if you knew that information, you could hard code it. So like on Windows, you can hard code your network information if you've been given it by your administrator. Or on Linux, you can edit this file and you can statically specify your machine parameters, the IP address, the subnet mask, the default router, the default DNS server. All of this stuff can be done manually, hard-coded in a file. But typically, if you're walking around with a cell phone or a laptop, typically what you would do is you would do something called DHCP, which is the Dynamic Host Configuration Protocol. You would ask for all of that stuff. You say, hey, I don't care what numbers I get, just give me something that gets me the internet. And that's what DHCP will do. It's typically used in wireless networks, and one of the big things that DHCP allows you to do is reuse addresses. So if someone from the previous class has gotten an IP address off of that base station, has left, you can come in here and use that same IP address after that person has left, and that's done through DHCP. Okay. Okay, so here's the scenario. So typically, before you join a network, somewhere on that network, someone is running some DHCP server software. And the server is listening on a very specific port, and it's looking for broadcast requests for host configuration information. So here on the right, we have 3 subnets, and on the right subnet, we have some DHCP server on it. We have some machine that will arrive onto this subnet, and it wants an address on this subnet. And of course, whoops, that's misnumbered. Needs an address on this 131.252.3.0/24 network. So that's a typo that I'm going to fix. Didn't quite get all of those things. And so what will it do? So you can see that some of these machines on here already have IP addresses. The DHCP server's got an IP address, but this arriving client doesn't. So this is what happens. And of course, that should be a 2, not a 5. You can't, so, yeah. All right, there's a lot of things wrong with this slide. That should be a 2. That's the 5, that's the 6. So the DHCP server has a 3.2 address. The arriving client comes in, and what it does is it broadcasts at the link layer this DHCP discover. It says, hey, I am looking for a DHCP server to get me an address, and it's a broadcast destination, and this is an IP packet that we're talking about here, and it uses a data link layer broadcast, and it says, the magic port that the DHCP server listens on is 67. It says, hey, I'm trying to get my configuration, send it to me. And then the DHCP server, hopefully there's only one of them on your network. If there's multiple ones, you got a problem. Hopefully there's one legitimate DHCP server who's going to say, oh, I'm the DHCP server. I manage all the IP addresses on this subnet. I am going to offer you this address, which is YI adder, and I'm going to give you 131.252.3.7. This is not yours yet. You have to claim it in order to own it, because you don't want someone to keep on asking the server for IP addresses and then not claiming it, because you'd like soak up all the IP addresses. So this is why there's a separate step. It offers you this IP address, and then you say, I want to claim that IP address. So you say DHCP request the IP address, 3.7, and then finally the DHCP server says, okay, you get that IP address, you can begin using it, and while I'm at it, I'm going to give you a whole bunch of other information that lets you operate on my network. So inevitably, this is what all of your laptops right now have already done for that base station up there in that corner. Okay, so this is actually the opposite of ARP. ARP is saying, hey, I have an IP address. What is its hardware address? DHCP is like, here's my hardware address. Give me an IP address, is effectively what's going on. So these two operations are happening on the link layer. Okay. So you get your IP address. That's one of the things that you get when you come onto the network. But in order to really function on the internet, you need to know other things. The first thing is, the next two things are a net mask and a default router. The net mask talks about what are the IP addresses that are directly connected to you on the same network. What is the range of IP addresses that if I have a packet for, I can just connect directly to that host. So, and we'll talk about the net mask in the IP section later. The default router says if I have a packet and I know it's not destined for someone on my network, who do I send it to? Like, I know Google is not on my network. If I have a packet for Google, yeah, give me the place that I need to send that to, and that's the default router. And then finally, I have google.com and I don't know what the IP address is. I need an IP address that can take google.com and give me an IP address. And that's what this default DNS server, and it's specified as an IP address. Okay? One of the nice things about DHCP is that once it's soft state, you're given an IP address for a short amount of time. And if you want to continue using that IP address, when you are towards the end of that time, you have to renew the lease. You're leased an IP address, and then towards the end of it, if you're still using it, your computer will automatically renew that lease so that you can keep on going. But if you walk away and you don't renew that lease, then that lease expires and then it can go to someone else. So that is the basic function of DHCP. Okay, so here's a question. What prevents someone from creating hundreds of virtual interfaces and hogging all of the addresses to him or herself? So I could have one laptop. I can say, I am all of these different hardware addresses. Give me an IP address. What would prevent that? The answer is nothing. This could happen if you wanted to wipe out a network. Okay, so we don't have a lot of, these are things that happen when you haven't considered an adversarial approach to networking. Okay, so I cover all of this. I want to cover Wireshark because as part of your ARP labs, you're just going to be looking at Wireshark output and being able to parse requests over the network going to and from a machine. Now, it might be rare for you to bring up Wireshark when you're developing an app, but if you have something going on where somehow the request that's being sent from client to server isn't what you thought it was, it sometimes is helpful to take a packet capture and see the payload, the exact payload of the bits on the wire going from client to server. Wireshark is a way for you to get that. And so this is what I want you to use for your lab. So it's the de facto tool for network monitoring. Anytime someone is doing network forensics, say you've gotten broken into, you've been keeping track of all the packets, it's typically kept in this PCAP file that Wireshark emits. It's the same format. So everyone uses this to basically do their network analysis. It's built on libpcap, which is a packet capture library for Linux. It does require administrator privileges to run because you don't want any regular user to start dumping the traffic of all the other users on that same computer. So you typically only allow super users privileges to that. It supports this thing called promiscuous mode. So typically, your network interface card will look at all the frames going by, and if it doesn't match its own hardware address, it'll be like, okay, I'm not going to process that. Promiscuous mode says, I'm really sneaky. I want to see everybody's packets. I don't care if it's destined for me or not. And this is what you can do. You can set up your network interface to see everything. So for example, you go into a cafe. It's an open wireless network. And you have a hardware interface for your wireless card, but you want to see all the packets that everyone is sending on that wireless network. You turn on promiscuous mode, your radio will capture every single frame and send that up to the host. So that's what promiscuous mode does. It supports all the major network protocols. So when we get to the transport layer and the HTTP layer, and when we talk about the newer protocols that are being deployed, it supports all of those. There are three main windows. When you pull up Wireshark for the first time and you start capturing packets, there are three windows. There's a top window that is basically a packet history, all the packets that it has captured. You can scroll up and down and see the packets that have gone by. There's a bottom window that has the raw packet payload. You click on a packet, and then on the bottom you see the raw payload, all the bytes in that packet. In the middle, there's this condensed, parsed header summary. It's basically the network, the headers, the protocol headers of every single layer is in the middle. Okay, so this is what it looks like. So this is the top. This is a packet history at 700 and this is 705th packet sent at 40 seconds. Has a source of 10.02.15. Has this destination. Has this protocol. Has that URL. And this is the payload. So you click on that, and these are the raw bytes of that particular packet. Moreover, if you see in the middle, you see the frame, outer frame, the inner, the top two are the frame, the IP header, the transport header, and then the application header. So you see all layers of that Russian doll that we talked about last class. And if you click on a header in blue, it will highlight the header bytes in the payload. And so you can see this is the data link. This is the Ethernet header that's associated with the packet that got sent. You go to click the Internet Protocol one, and this is the IP header that is the next layer of the doll. And then finally, you click the TCP header, and you get the TCP header here. So this is the outer layer, the next inner, the transport layer. And then finally, you get the hypertext transfer protocol. And this is the application data. And you can see, if you've got good eyes, well, you barely see that. You can see the GET request for the main web page. You can see all the HTTP headers. So as part of HTTP, we'll cover this in 2 classes. All of the different headers that are sent with HTTP, you can see exactly what has gone on in that transaction. And if there is some kind of error in any of this, you can then trace it back and debug your application. Okay? Okay, so then this allows you to do the ARP labs, which are over here. Whoops, that's not it. So if you go to the lab site, so the first thing that I want you to do is install Wireshark. And this is why people asked if they could do this on a Mac. If you can install Wireshark on a Mac, that's fine. But if not, do this in the Linux VM. You have to do, so install Ubuntu, and this is the way you install packages in Ubuntu. So you install Wireshark. You can use I want you to use the ifconfig command on Ubuntu to get all of the network interfaces, to get all the information you can on the network interfaces for your virtual machine. This is a typical troubleshooting command for networking on Linux. And then I want you to perform a netstat-rn. This dumps the routing table for your Linux machine. And we'll talk about this when we get to the networking section in a second. And then I want you to ping the default router and then use the ARP command. So the ARP command dumps the hardware addresses of the addresses in the ARP table. And I just want you to see all of these things in action to get an idea of what's going on. And then I want you to perform the Wireshark capture, and I want you to start pinging google.com and seeing these frames go by in Wireshark, and then just pulling stuff out of it so that you can feel comfortable navigating a packet capture, which is, I would say, a good skill to have coming out of a computer science program. So that's the lab. So it's not it won't take you that long, but it's a useful set of tools to learn. So with that, that's the data link layer. Are there any questions about? There's not a lot in it, so that's why I'm going to move to the next thing, unless anyone has any questions. Yeah. Uh-huh. You can get the encrypted frames, but then you would have to decrypt it. So typically a network interface, it's trying to save the operating system overhead. Like if it sees a frame and it knows that it's not meant for that particular host, it'll say, I'm just going to drop that at the interface card itself. If you turn on promiscuous mode, then you have explicitly said, I want to see everything. I don't care whose it is. But hopefully it's encrypted. So hopefully it is WPA. But if you're on an open wireless network and you're like, I want to see how much stuff I can get from other people, then not that I'm condoning that at all, but you could do that. And then you would turn on promiscuous mode and get everybody's stuff. And there are some adversarial tools. So if you take the web security class next quarter, there are tools that's what they do. They go and they used to go and try and hijack people's social media accounts by going to an open access point, getting all the cookies going by, and then just hijacking the session of whoever's in that coffee shop. So yeah, that's definitely an issue that hopefully none of you make the mistake of doing now.